Welcome back to the Weights and Measures Primer. This is Ross Anderson, and in this video I'll be discussing the topic of verification. What is it? Seems like a very simple question. We've been using the term verification for probably 35 years in weights and measures in the United States, but I'm going to suggest that we really haven't grasped entirely what it is. The subject today will primarily be what is tolerance verification. That is verification of accuracy. To give you a hint of where this is heading, I'd like to draw your attention to the title of a very important weights and measures document. We know it as ISO 17025. It's the general requirements for the competence of testing and calibration laboratories. And my question is, why did they differentiate testing and calibration? Why didn't they mention verification? I think when we get all done, a lot of this will make sense. A good place to begin, of course, is with a definition. Here we have the definition of verification adopted by the NCWM in 2005. It's a formal evaluation of something against specifications and tolerances for determining conformance. So as we look at this, there are two pieces. There's a specification piece and a tolerances piece. On the specification side, we have technical requirements regarding design, construction, and function. And the way we verify is through this action we call inspection. On the tolerances side, we have performance requirements regarding precision and accuracy. And what I really want to address is what goes here. What actions go in this box? One of the words that immediately comes to mind is, of course, calibration. Here we have 4 uses of the word calibration in a chain. The metrologist calibrates a slicker plate standard. This is typically a working standard in the lab. The metrologist uses that slicker to calibrate 2 test measures. One of those test measures belongs to a service technician who uses it to calibrate a fuel dispenser. And finally, after the placed in service report is received, the inspector is sent out to use the other test measure to calibrate that same dispenser. The issue is what's going on behind the scenes. What we see is the metrologist, in calibrating the slicker plate, took an action to precisely define the quantity and uncertainty. When that slicker was used, it was used to precisely identify quantity and uncertainty of the test measures, to verify conformance of the test measures, in this case with Handbook 105-3, and to adjust performance where needed. That's why it's in parentheses. The service technician undertook actions to verify the conformance of a dispenser and to adjust the performance if necessary, again, if needed. The inspector, on the other hand, in using calibration, only took actions to verify conformance. So you see 3 principal nuances of meaning in this word calibration in the way we use it. However, if we go back to the definition that was adopted by the NCWM, you can read this and see that the definition means to precisely define quantity and uncertainty. There's no mention in this definition of verifying conformance or adjustment, and this is really important. If we follow the definition and break it down into its component pieces, the first step is to take a standard where we have a quantity value and an uncertainty value assigned to that standard. We take a process, a measurement process where we know the uncertainty, and we produce indications. These are the 4 pieces mentioned in step 1 of our definition. In step 2, what I'm calling data reduction, we take those 4 pieces of information and we produce a new measurement result, which is a quantity and an uncertainty assigned to the instrument I. The quantities are simply the sum of the quantity of the standard and the quantity of the difference, the indications from the measurement. The uncertainty, however, is not just a simple addition. The uncertainty is produced by the root sum square method. There are two kinds of uncertainties in step 1. There's an expanded uncertainty associated with the standard and a standard uncertainty associated with the measurement process. And what we have to do is put them all in terms of standard uncertainties. So we divide the expanded uncertainty by 2, then we combine them, and then we multiply the total again by 2 to get an expanded uncertainty. The critical thing here is for a calibration of an indicating instrument, let's say a tape measure or a meter, this would imply multiple values for quantity and uncertainty over some operating range. But the critical thing about calibration many people miss is that the user decides how to use this information. The calibrating body makes no decisions. They simply report data. Now, if we go back then to our definition of verification, well, this requires someone to make a determination of conformance. And I'm going to use the term compliance for conformance because it's a legal term under legal metrology. We could add a third step to our calibration to make it a calibration verification, so we now make a compliance decision. But with calibration, the decision rules, which are stated as part of the accuracy requirements, include explicit treatment of uncertainties. I looked at a number of standards to try and find a good example of this, and the best one I think that I found in my simple search was R111. This is the test weights standard in the OML system. In section 5, we see first in section 5.2 that the expanded uncertainty must be less than 1/3 of the prescribed tolerance, or maximum permissible error in their terminology. It then goes on in 5.3.1 to say that when you apply the tolerance, you must reduce the tolerance by that measurement uncertainty, and this gives you an enforcement tolerance that is actually smaller than the actual tolerance. That's all well and good in the lab. What happens when we get out in the field? Well, there's a great hurdle for us to cross out in the field, and that hurdle is basically that we can't find this U/P term, and without it we can't find the uncertainty of the instrument. So what does it take to find this process uncertainty? Well, first you have to recognize the variables. The standard, the instrument, the procedure, the environment, and the person making the test are all variables. And the way we monitor process uncertainty is through two general tools: internal controls, external controls. Internal controls are control charts that measure repeatability of a process over time using a check standard, and that also includes the influences that are going on around the test. The external controls, these proficiency tests, look for biases. The simple fact is that if we try to duplicate this in the field setting, with each person, instrument, procedure, and environment being unique, we would literally be making control charts for each instrument that we test. And the fact is, calibration verification is not what's done in the field. And how do we know that? Well, let's look at the compliance decision in Handbook 44. Here we have the definition of accurate. So a piece of equipment is accurate when its actual value, as determined by tests made with suitable standards, conforms to the standard within the applicable tolerances and other performance requirements. My question to you is, what about the uncertainty? If in fact we were applying calibration verification, then there would be some expression of the uncertainty here, but it's simply not there. The other thing I'd point out about this definition is this word standard. Now, standard is singular, which means it's not the same standards that you see 4 words earlier. This standard is something else. So maybe we need to look further in Handbook 44 to find out what this standard is. And I looked at the definition of excess and deficiency. These are errors of excess and deficiency. And that's whether its actual value is respectively greater or less than its nominal value. And if you look up the word nominal, you see the word intended. So I'm going to use intended. It's in excess or deficiency whether it's greater than its intended value. All right, that's great, but what's intended? It's the same as the standard up in the definition of accuracy. How about the other type of errors, over-registration and under-registration? This is where indications are respectively greater or less than they should be. Well, what should be? I hope you see that there's a missing piece here. What is the standard for accuracy? How do we find this intended value for excess deficiency should be for over or under registration? Essentially, we're asking what role does measurement uncertainty play in the compliance decision? And I suggest if we don't know the uncertainty, we're not using calibration verification. This is a definition of verification taken from UWML, the International Vocabulary of Measurement, 3rd edition. And you see this is very similar, but it doesn't split the specified requirements into two pieces. But what's interesting about this definition is number 5, note 5, where it says verification should not be confused with calibration. And I think that's what we explained earlier. If we now move to R76 and look at the errors and the definition of accurate, we see that errors are the indication of the instrument minus the conventional true value of the corresponding mass. And the maximum permissible error is the maximum difference, the maximum error of indication. But it's relative to the corresponding true value. So again, you see we've given this true value a name. And if we compare this to Handbook 44, the definition of over-registration and under-registration, the should-be value is now in UWML, this conventional true value. And if we look at the definition of accurate, this is replacing standard. But now we need a definition of conventional true value. That again we find in the International Vocabulary of Measurement, and it's a quantity value attributed by agreement to a quantity for a given purpose. What is this attributed by agreement? Well, interesting enough, this means a bunch of people got in a room and voted on it. This isn't agreement with international standards. This is an agreement between people. Now it's interesting that you see in Note 1, the conventional true quantity value is sometimes used, but its use is discouraged. Well, I think it's interesting it's discouraged, and yet if you look in R111, R76, R105, which is mass flow meters, and R117, which is liquid measuring devices for things other than water, just to name a few, you can see that the term is used in UWML documents. The key thing about this note, note 3, is that a conventional quantity value is accepted as being associated with a suitably small measurement uncertainty. It's interesting, it doesn't say how you got there, just we agree it has a suitably small measurement uncertainty. This one comes from the GUM, the Guide to the Expression of Uncertainty in Measurement. And again, we see accepted sometimes by convention as having an uncertainty appropriate for given purpose. And it is interesting in Note 2 that a number of results are sometimes used to establish a conventional true value. So now I need to introduce you to what I'm calling the testing verification process. Like the calibration verification process, there's 3 steps, but these 3 steps are quite different. In step 1, we qualify the standard. In other words, the standard has to meet certain requirements that involve its quantity and its uncertainty. Once the standard is qualified, we move to step 2. We measure the error, this E sub I. That's the important thing that is used in step 3 in the compliance decision. What's interesting is the Q sub T, the true value. QT is the conventional true value of the input quantity obtained using the specified standard and the designated test procedure. The Q sub T forms a triad with the indication of the instrument. So error is always a function of Q sub T and the indication. For delivery error, it's Q sub T minus the indication. For indication error, it's indication minus Q sub T. And by convention, Q sub T has a suitably small measurement uncertainty for the purpose. Now, we do this 2 ways in Handbook 44. One is what we call no correction. So in this case, in the measurement step, we use the nominal value of the standard, and both the quantity and uncertainty of the standard are considered in the qualification step. This is the preferred method in Handbook 44, according to Appendix A. There is a not preferred method that's still accepted, where you include the correction. If you do that, you only have to consider the uncertainty in the qualification of the standard. What's critical is that you see there's no uncertainty in the measurement and no uncertainty in the compliance decision. What we're saying is the uncertainty in this test is implicit in the true value Q sub T. Here's an example using 2 measurements, our test of a fuel dispenser. It's interesting to see that we pass knowledge from the test measure, our reference standard, to the artifact test liquid, which is a transfer standard, and it's the Q sub T assigned to the transfer standard that is compared to the dispenser indication. Each arrow represents a separate U sub P term that is unknown, and this includes short-term, long-term variability, and bias. And what's interesting is the process variability is masked often by the instrument variability, the repeatability of the instrument, which is usually much larger. Finally, I'll show you this is 6 measurements of verification in a gravimetric test. For example, we might do this for an asphalt meter or something like that. What's interesting about this is you have 6 measurements, you have 4 different transfer standards, and what you have to do is you have to take the true quantity value is Q1 times Q3 divided by Q2, and that's what gets compared to the meter indication. Coming back to the very beginning of what were the objectives, why was testing and calibration separate? Because they different approaches to uncertainty. Testing represents the uncertainty implicit approach using the conventional true value, and calibration uses the uncertainty explicit approach where we use the uncertainty in the decision rules. And as we see, Handbook 44 uses testing verification, and Handbook 105, for example, uses calibration verification. If you want to see how this works with R111 and R76, that's weights and weighing instruments, we see that the uncertainty explicit approach is used in R111. So we have F1, F2, M1, M2, and M3 standards. We would take the F2 out in the field to test Class 2 instruments under R76, or we would take M2 out to test Class 3 under R76. There is a second key difference between testing in Handbook 44 and calibration in Handbook 105. And that is in field testing, measurement and adjustment is made at ambient conditions. And GUR 43 requires adjustment as close as practicable to 0 error. That means at ambient conditions. In lab calibration, in contrast, measurement and adjustment are made at reference conditions. 105 series has a provision similar to GUR 43 in terms of adjusting as close to 0. When we adjust at reference conditions, I like to think of this as we establish one truth. All adjustments are made at the reference conditions, and that means that all of them are on the same basic truth. In this case, you can see if the top and bottom of this rectangle represent the maintenance tolerance of the device, you can see that the errors of the individual weights in the calibration verification, for example, are within 1/10 of the maintenance tolerance. Think of it as a convention that we accept multiple truths, and this is the way our convention works. The blue line is the NTEP test, where we adjust to 0 at reference conditions. We require that all values be within acceptance tolerance over the range of the influence. The red and green are adjusted at extreme ambient conditions in field tests. Notice that all of the values now fall within maintenance tolerance. But if we were to bring these instruments back to reference conditions, all of the values would be within acceptance tolerance. These two differences that I've spoken about are not the only differences between testing and verification, and I found this table in an article by Summer and others called Error Limits and Measurement Uncertainty in Legal Metrology, readily available on the internet. Great article on similar things. They only had 2 columns. They were only talking about the 2 right-hand columns, but I added calibration and I added a few rows. Let me begin by looking at calibration. Calibration is driven by customer demands. It's done in the laboratory, and the starting reference is always a calibrated standard in base units. Now, base units are what we call SI units, all traceable to the SI, but not conventional. Conventional units are like conventional mass and other units where we take certain shortcuts. Now, what's important about calibration is you adjust and test at reference conditions. You report quantity and uncertainty to meet customer demands. The decision rules are user-specific and are actually made by the user. And the validity is at the time of test and under specified condition. Traceability is interesting because the lab is the one that provides the proof, and that's in the form of an accreditation or an audit. What we're interested in, though, is calibration and testing verification. And as you compare these 2 columns, I think you'll see some of the differences that we've pointed out and some other differences. Calibration verification is done in the lab. Testing can be done in the lab or the field. We use a calibrated standard in base or conventional units for calibration, but basically it's a calibrated or verified standard in conventional units in testing verification. Reference conditions are for the calibration, but ambient conditions for testing. When it comes to the report, the calibration is usually a quantity and an uncertainty, but that's optional in the case of verification because what's important is the compliance. You may have the quantity and uncertainty in the raw data, in the lab data, and not necessarily on the report. The same thing with errors in testing verification. You don't necessarily have to report what the errors were, you simply have to report the compliance. The decision rules, as I discussed, are explicit uncertainty in calibration, but implicit uncertainty in the testing. Now, the validity for both of these is for the period set in the legal requirements. And finally, as far as traceability, if you're doing a calibration verification, the lab has to provide the proof. But in testing verification, all you have to have is a traceability certificate for the standard and knowledge that you followed the procedure. I would like to fill the holes in Handbook 44, and that was my 2020 proposal, to define the conventional true value, and that's basically the value found using the specified standard and the designated test procedure. Need to redefine accurate in terms of this conventional true value, replacing the word standard. We need to include the term conventional true value in the specification of tolerances in GT3 or perhaps in the definition of the error types. Also consider adding testing verification to the fundamental considerations in Section 3 and also changing some of the parts of Section 2 where it gives the idea that maintenance tolerance is there for instrument drift. whereas what I showed is that influences is the main reason that we have maintenance tolerances. The final thing that I think we need to realize is there's a really important unanswered question about testing verification. If we do not know the uncertainties involved, can we have confidence in the results? Well, I'm going to address that in the next video because this one's already running long. But I will give a hint. Calibration verification focuses on individual trees, while testing verification focuses on the forest. Well, that's what verification is. I hope this has been enlightening, but I do think it's important to note that we really need to do better in our training to make sure that the definition of calibration that we teach our inspectors and teach our service people that follows the definition that the NCWM has adopted, the precise definition of quantity and uncertainty. And make sure that we use verification and testing when we talk about Handbook 44.